Okay, so good afternoon. This afternoon we are talking a little bit of motor control, and in particular we are focusing in this presentation on the solution that ST has to drive a three-phase motor, brushless, with internal permanent magnet. ST has a long story about the support of such kind of motor, and the first release was in the 2009, and each year we provide always new feature for this kind of library. And one new feature that we will show in the next version of the library will be what we call motor profiler. First of all, we need to understand why we need a motor profiler. Sometimes, and when you work with the motor control, you can see that sometimes it is hard to start with a new motor, because you need to first to measure the motor parameter, and you need to have some, let's say, specific skill or equipment. Sometimes the tuning of the regulators that is inside of the algorithm can be empirical, and you need to find the proper acceleration for the startup phase according to the load, and this can be difficult. And we can have a lot of trial and error before to start with the control of the motor. Okay, why we need to measure the motor parameter? Because the field-oriented control algorithm is using a model of the motor, so it requires to know which is the electrical characteristics of the motor. So it is also needed to tune the current regulators and to tune the sensorless algorithm that runs the motor in sensorless control. Then we have also to know which is the electrical motor parameter to tune the speed regulator. So all of these parts of the code requires the specific measurement of the motor characteristics. So let's say that this information is mandatory to be known by the user before to configure the motor control library as it is. Okay? So to help to the customer to resolve this kind of problem, we implement the new feature that we call motor profiler. The motor profiler is a set of algorithms that performs the automatic measurement of the motor parameter directly on the system. So it performs the measurement of electrical parameter, so stator resistance, inductance, and back EMF constant. Then it measures also the mechanical parameters of the motor according to the load, so the inertia and friction coefficient. Then automatically perform the tuning of current controller and the sensorless algorithm. So basically we can run any motor in a few seconds. And another thing that I wanted to underline is that there is no need to additional hardware. The same hardware that is needed to run the motor is sufficient to perform the automatic measurement of the motor. So there is no need of extra hardware in order to use this feature. And today we will see, let's say, a little bit how this new feature works. What is the magic that is behind this feature? So first of all, some things that cannot be measured. Okay, are few parameters and simple parameters that anyone can knows about this motor. So we don't ask to have, let's say, the measurement of resistor or inductance, but we ask to the user to insert in the configurator, which is the number of pole pairs of the motor, which is the, let's say, the application maximum speed on which the customer wanted to run this motor, and which is the nominal current of the motor, because it's not possible to measure the nominal current of the motor. And if it is the case, also the user can insert which is the anisotropy of the motor. Okay. Just a note: the algorithm is able to measure which is the nominal speed of the motor on the fly. Okay, and while the parameter that we ask to the customer is the desired maximum speed, is to make a check if the desired speed of the application match with the motor that we are using. Okay, sometimes it can occur that the customer wants to run at 10,000 of RPM and the motor cannot reach that speed. So it is just for a dual check. So the motor profiling algorithm is done with a number of steps. We start with known, we don't know which is the parameter of the motor, and at the end we will complete with a fine-tuned system. Okay, so the first thing is, let's say, to measure the electrical motor parameter. So I repeat, no additional hardware is required. How it is done, the measurement? Of course, applying some voltage. We have an inverter, so we can apply some voltage, and we can measure the current that flows into the motor. It is the same, let's say, current sensing network that is required to drive the motor. So basically, we do the same thing. So to apply the voltage, we use to apply the classical PWM generation, and we measure the DC bus voltage in order to convert the duty cycle applied into a voltage command. In this way, so basically is done the measurement of the motor electrical parameter. And to achieve the measurement of the stator resistor and inductance, it is used an unidirectional current generation, while during the run of the motor we provide the sinusoidal waveform. During the measurement we apply a unidirectional current measurement. So the first step, since the parameter is unknown, is the first step is to determine which is the voltage to be applied to reach the desired measurement current. So we asked to the customer which is the maximum current for that motor, and we need to understand which is the voltage that we can provide in order to reach that measurement current. And another important step is to align the motor in a proper direction, and with this kind of control it is automatically done. So just to underline that the measurement of the stator resistance and the inductance is done with the motor in still condition. Okay. The measurement of the motor inductance is done through the measurement of electrical time constant. So we can provide a set of voltage pulse, and we can measure the electrical constant time of the system. And with this kind of measurement, it is possible to measure the inductance of the motor. When both motor resistance and inductance is measured, now it is time to tune the current regulator. So we have all the information to tune the current regulator. And this is done automatically by the firmware, calculating the proportional and integral terms of the current regulation, IQ and ID current regulation, in order to achieve a specific bandwidth of the closed loop system. So the user need only to, let's say, to define which is the closed loop bandwidth of the current regulation, and the algorithm performs the computation of the proportional and integral coefficient. Okay, for the not skilled people, this means that you have to set which is the strength of the current control, if you want a strength control or a relaxed control. So defining the bandwidth of the PI controller means just to have a single knob, slow, medium, hard control, okay? Just to understand which is the difficulty to set up this system. When the current controller is tuned, at this moment it is possible to start up the motor. We start up the motor generating an acceleration, a current, three sinusoidal current. This produces a rotating field, and the motor will follow this field. So this is an open loop phase in which the motor starts to run. It is the same approach that we use when we start the motor with sensorless control. So the first phase is an open loop startup, and we use the same approach to bring the motor at a certain speed. Why this? Because we needed to measure the last important parameter, that is the back EMF constant. And the back EMF constant is measured if there is some back EMF. Back EMF is voltage that is induced into the stator when the motor is running. So it is not possible to do this measurement in standstill. So we have the possibility to measure, to estimate the voltage constant, the KE parameter, when the motor is run in open loop, okay, using the model of the motor, and knowing its resistance and inductance, because we already have measured it, okay? So at the end of this step, we have measured the KE. And at this point, we can, let's say, start up the motor, okay? But we need the last step. An important step is to tune the speed control loop. At this moment, we don't have, okay, we have measured the motor parameter and we can run the motor, but the speed control loop is not already tuned, okay? We call this second part of the algorithm as one-touch tuning feature. This means that with a single parameter that can be inserted by the user, it is possible to fine-tune the speed controller automatically with automatic measurement done by the firmware. So the user can set which is, let's say, the kind of load that he has in the system. If there is a motor with no load, medium load or big inertia motor. And this can help the detection of the mechanical parameter of the motor. Of course, if, let's say, the user don't set the proper value of this parameter, is not so much important, because we test all of the conditions. But if you set the proper parameter here, you have a more fast measurement of the parameter. Okay, to do this, we have, let's say, the mechanical motor parameter. It is a first order system with the inertia plus frictional part. And modeling the system in this way, it is possible to measure the two parameters. For instance, the inertia of the motor can be measured applying a step variation in the current, in the torque, and measure the time constant. So the measurement of the mechanical time constant is used to measure the inertia of the motor in a similar approach that we do with the current. So for the current, we measure the electrical time constant. For the inertia, we measure the mechanical time constant. But the approach is very similar. And also, it is similar approach to tune the speed regulation. So we have, let's say, the speed regulation algorithm. We have measured the inertia of the motor and the frictional coefficient, and then we can set up automatically the proportional and integral terms of the speed regulator starting as input with a single parameter, that is the bandwidth of the closed loop system. And here we have the speed regulator closed loop bandwidth in order to set up which is, let's say, the bandwidth of the speed regulator. And this parameter is the one knob that we mentioned before in the previous slide. So basically, we can set here which is the strength of the speed controller. So putting together the two features, we have the motor profiler plus the one-touch tuning. We can achieve the results of spinning the motor in, let's say, less than 1 minute. Okay? So the first step is with motor stopped to measure the stator resistance, the stator inductance, and to tune the current regulation. In the step 2, we start the motor in open loop, and we can perform the KE measurement, so the back EMF measurement, and we can tune, set up the sensorless controller, and we switch over from the open loop to the closed loop control in order to perform the last part of the tuning, that is the measurement of the frictional coefficient, of the moment of inertia of the system, and to tune the speed regulator. And you can see that in, let's say, 60 seconds, it's possible to start the motor from, let's say, unknown condition to fine-tuned condition. Okay, just few words about the workflow that we implement in the library. Okay, we have the motor control library. We have a PC software tool that is used to configure the library. Okay, in this software tool is called MC Workbench, STMC Workbench, Motor Control Workbench, and you can create a new project inside the ST Motor Control Workbench. You can define which is, let's say, the hardware that you are using and so on. Then you can enable the new feature, the motor profiler. If you enable this feature, the algorithm is compiled into the code, and when you start the motor profiler, this algorithm is executed to detect the motor parameter and to run the motor. So you can start the motor profiler from the workbench, and you can run the motor. Then, at the end of this procedure, the firmware has calculated the parameter. So you can take from the firmware this value. So the workbench is able to take this parameter from the firmware and configure the project in order to use this parameter. In this way, it is possible to disable this feature and to reduce the code size. And at the end, you will have, let's say, the standard compact firmware to drive the motor. But let's say you have used the motor profiler feature to identify the motor parameter and tune the system without need to be, let's say, skilled or have specific instrumentation. And it is a very fast way to propose our solution for the customer. Okay. That's all for my presentation.